All right, check the perimeter. Yes, sir, looks clear.
Summer 1943. Kummersdorf Proving Ground, Germany. A team of German engineers gathered around a captured American M4 Sherman tank, preparing for detailed technical analysis. This particular Sherman had been captured in Tunisia after fighting through thousands of miles of desert warfare. The engineers expected to confirm German superiority. German tanks, Tigers, Panthers, Panzer IVs were heavier, more powerfully armed, better armored. The Sherman was known to be inferior in direct combat. Its 75 mm gun couldn't penetrate heavy German armor at combat ranges. Its armor was thinner. Its profile was taller, making it an easier target. The analysis should have been straightforward. Document American technical inferiority. Confirm German engineering superiority. Write a report. But as the engineers disassembled the Sherman, studied its components, examined its systems, they discovered something that challenged fundamental German assumptions about tank design. Oberingenieur Heinrich Müller's report, July 1943, archived at Bundesarchiv. The American M4 Sherman represents a fundamentally different philosophy of armored vehicle design, where German tanks prioritize combat performance, firepower, armor protection, battlefield superiority. The Sherman prioritizes operational availability and mechanical reliability. Initial assessment. The Sherman is inferior in direct combat specifications. However, detailed examination reveals design features that may explain American operational success despite technical inferiority. Most significant finding: the Sherman is designed to be maintained and repaired by soldiers with minimal technical training using basic tools. German tanks require specialized mechanics and factory-level facilities for many repairs. Recommendation: German tank design should incorporate lessons regarding mechanical reliability and field maintainability. Current German tanks offer superior combat performance but suffer excessive mechanical failure rates that reduce operational availability. This was not the report German command wanted. They wanted confirmation that German tanks were superior in all ways. Instead, they got an uncomfortable truth. The Sherman was designed to survive logistics and maintenance challenges that German tanks couldn't overcome. This is the story of what German engineers discovered when they examined captured Sherman tanks, how American industrial philosophy challenged German engineering perfectionism, why the tank that lost on paper often won in reality, and the one thing about the Sherman that German engineers simply could not believe: that American factories built tanks like Detroit built cars, with interchangeable parts from 11 different manufacturers producing identical components that could be swapped without modification. The context: German tank superiority on paper. To understand what shocked German engineers, you need to understand what they expected to find. German tank philosophy in 1943. German armor design emphasized heavy armor, thick steel plates that could withstand enemy fire. Tigers had 100 mm frontal armor. Panthers had 80 mm sloped armor. Powerful guns, long 88 mm and 75 mm guns, capable of penetrating enemy armor at long range. Tigers 88 mm could kill Shermans at 2,000 plus meters. Engineering excellence, sophisticated mechanical systems, advanced transmissions, precision-engineered components. Combat superiority: German tanks were designed to win tank vs tank battles through superior firepower and protection. The Sherman specifications, M4A1 1943. By comparison, the Sherman seemed inferior. Armor: 50 mm frontal armor, sloped, sides 38 mm, much thinner than German heavy tanks. Gun: 75 mm M3 gun with mediocre armor penetration, could not reliably penetrate Tiger or Panther frontal armor at combat ranges. Profile: relatively tall for a tank, presenting a larger target. Speed: fast for operational mobility, 26 miles per hour road speed, but not significantly faster than German tanks. On paper, the Sherman lost. Head-to-head, a Tiger or Panther would typically defeat a Sherman. The German tanks could engage at longer ranges with more powerful guns and survive return fire with thicker armor. German engineers knew this. German tankers knew this. Allied tankers knew this too. So when German engineers examined a captured Sherman, they expected to document technical inferiority and confirm German superiority. What they found instead challenged everything. The first shock: mechanical reliability. The first surprise was how far the captured Sherman had traveled without catastrophic mechanical failure. The Sherman's history. This particular Sherman, based on markings and maintenance logs captured with it, had traveled over 5,000 miles in combat operations, operated in North African desert conditions, extreme heat, sand, dust, received field maintenance by crew and battalion mechanics, no factory-level repairs, remained operationally available for majority of its service life. German engineer observations. From Kummersdorf Technical Analysis. Engine: Continental R975 radial aircraft engine, gasoline-powered. After 5,000 plus miles of operation, engine shows wear but remains functional. Could likely continue operations with basic maintenance. Transmission: Synchromesh transmission, relatively simple design, shows wear consistent with heavy use but no catastrophic failures. Easily accessible for maintenance, simple enough that crew-level repairs are feasible. Suspension: vertical volute spring suspension, VVS, simple, robust, easily repaired. Springs show wear, but system remains functional. Tracks: rubber block tracks show significant wear but remain operational. Track replacement is straightforward and can be performed by crew without specialized equipment. Overall assessment: this vehicle has endured operational conditions that would have resulted in multiple catastrophic failures in comparable German tanks. The Sherman's mechanical reliability appears to be a designed feature, not an accident. The comparison to German tanks. By 1943, German tank reliability was becoming a serious problem. Tiger I, Panzerkampfwagen 6. Transmission failures common after 400, 600 miles. Engine overheating in extended operations. Complex repairs requiring specialized mechanics and equipment. Operational availability often below 50%. Panther, Panzerkampfwagen 5. Early models plagued by engine fires and transmission failures. Final drive failures common, would break under combat stress. Operational availability catastrophically low during initial deployment. German tanks were mechanically sophisticated but fragile. They required specialized mechanics with extensive training, factory-level repair facilities for many failures, specialized tools and equipment, extended downtime for repairs. The Sherman was mechanically simple but robust. It required basic maintenance by crew or battalion mechanics, field-level repairs for most failures, standard tools available to any unit, minimal downtime for repairs. The second shock: interchangeable parts. The discovery that shocked German engineers most was the Sherman's parts interchangeability. What German engineers found from detailed Kummersdorf analysis. Most remarkable finding: Sherman components are manufactured to such precise tolerances that parts from different manufacturers are completely interchangeable without hand-fitting or modification. We removed the transmission and installed a spare transmission captured from a different Sherman destroyed in Sicily. The fit was perfect. No modifications were required. Installation was completed in 4 hours by 3 mechanics with basic tools. This suggests American manufacturing capability far exceeds our estimates. The ability to produce identical components at multiple factories with such precision that no hand fitting is required represents industrial capability we cannot match. German practice requires hand fitting of components during assembly. Even parts manufactured at the same factory often require modification to fit. The American achievement of true interchangeability across multiple manufacturers is unprecedented in our experience. The American industrial system. By 1943, Sherman production involved 11 major manufacturers: Chrysler, Ford, General Motors, American Locomotive Company, Baldwin Locomotive Works, Federal Machine and Welder, Fisher Tank Arsenal, Lima Locomotive Works, Pacific Car and Foundry, Press Steel Car Company, and Pullman Standard. Standardized components: engines, transmissions, tracks, guns, radios, periscopes, all manufactured to specifications so precise that components from any manufacturer fit any Sherman without modification. The assembly line approach: automotive industry techniques applied to tank production, division of labor, and specialized manufacturing. Quality control, ensuring dimensional accuracy. Mass production volumes impossible with traditional methods. The result: over 49,000 Shermans produced during the war. Replacement parts available from any source. Field repairs accomplished with standard components. Logistical simplicity: any spare part fits any tank. Why this shocked German engineers? German tank production was artisanal by comparison. Each factory had slightly different manufacturing methods. Components often required hand fitting during assembly. Parts from one factory might not fit tanks from another factory. Field repairs complicated by parts incompatibility. Quality control based on skilled craftsmen, not precision manufacturing. Oberingenieur Müller's assessment. The Americans have achieved what we believed impossible: true mass production of armored vehicles with complete interchangeability of components. This is not simply manufacturing competence, this represents an entirely different industrial philosophy. German tank production emphasizes individual craftsmanship and engineering excellence. Each tank is, in some sense, unique. American production emphasizes standardization and repeatability. Each Sherman is identical. In terms of individual tank quality, German tanks are superior. In terms of industrial efficiency and logistical simplicity, American tanks are incomparably superior. This has profound implications for sustained armored warfare. We can build better tanks individually. They can build adequate tanks in overwhelming quantities with logistical advantages we cannot match. The gyroscopic stabilizer, shooting on the move. Another discovery that impressed German engineers was the Sherman's gyroscopic gun stabilizer. The technology. The Sherman 75mm gun was equipped with a gyroscopic stabilizer that kept the gun relatively steady while the tank moved. This was a vertical stabilizer only. It didn't stabilize horizontal traverse, but it was revolutionary nonetheless. The tactical advantage. With the stabilizer, Sherman crews could fire while moving. Accuracy was limited but possible. Sherman crews could stop, acquire target, and fire faster because the gun was already roughly on target. In short-range engagements where first-shot advantage mattered, the stabilizer provided critical seconds. Without the stabilizer, German tanks had to stop completely to fire accurately. After stopping, crews had to manually lay the gun on target. This process took additional seconds. German assessment from Kummersdorf Technical Analysis. The gyroscopic stabilizer represents sophisticated engineering applied to practical tactical problem. While the stabilizer does not permit accurate fire while moving at speed, it provides significant advantage in shoot-on-the-move engagements and reduces time to engage when stopping to fire. German tanks lacked this technology. Our doctrine emphasizes long-range engagement where tanks stop to achieve accuracy. American doctrine appears to emphasize close-range maneuver, where shooting while moving provides tactical advantage. The stabilizer explains American tactical success in terrain where long-range engagement is impossible. Forests, urban areas, broken terrain. In such conditions, Sherman's ability to shoot while moving partially compensates for inferior armor and firepower. Why Germans didn't adopt stabilizers? Despite recognizing the stabilizer's value, German forces never widely adopted gyroscopic stabilization. German doctrine emphasized long-range engagement where stabilizers provided less advantage. Manufacturing complexity and resource constraints. Focus on firepower and armor rather than fire control systems. By the time the value was fully recognized, German industry couldn't afford the development. The power traverse, another American advantage. Related to the stabilizer was the Sherman's power traverse system for the turret. The system. The Sherman used an electrical or hydraulic power traverse system, depending on model, that allowed the gunner to rotate the turret quickly and smoothly using a control system. German tanks. Most German tanks used manual traverse, requiring the gunner to physically crank a wheel to rotate the turret. This was slow, especially for large turrets on heavy tanks. Exhausting for gunners in extended engagements. Imprecise for tracking moving targets. Some late-war German tanks added power traverse, but it was not standard. The tactical impact. Power traverse allowed Sherman crews to acquire targets faster, track moving targets more effectively, engage multiple targets in sequence more quickly, reduce gunner fatigue in extended combat. German engineer observations. The power traverse system provides significant tactical advantage in short-range dynamic engagements. Combined with gyroscopic stabilizer, American crews can engage targets faster than German crews in certain tactical situations. This partially explains American tactical success despite inferior armor and firepower. In close-range engagements where speed of target acquisition matters more than penetration capability, Sherman's fire control systems provide advantage. The reliability crisis, German tanks failing. While examining the Sherman, German engineers were acutely aware that German tanks were suffering catastrophic reliability problems. The Panther disaster at Kursk, July 1943. The Panther was rushed into service for Operation Citadel, Battle of Kursk. Results were catastrophic. 200 Panthers committed to battle. Within first day, over 160 were inoperative due to mechanical failures. Engine fires, transmission failures, suspension breakages. By end of operation, Panthers had higher losses to mechanical failure than to enemy action. The Tiger I's chronic problems. The Tiger I, Germany's most feared tank, was mechanically unreliable. Operational availability typically 30 to 50%. Transmission and final drive failures common. Required extensive maintenance after every operation. Many Tigers lost due to breakdown rather than combat, the fundamental problem. German tanks were over-engineered and under-tested. Complex mechanical systems. Tight tolerances requiring precision manufacturing. Advanced technology that required specialized maintenance. Designs rushed into production before thorough testing. The Sherman comparison. While examining the Sherman's simple but robust systems, German engineers recognized their tanks' weaknesses. Sherman advantages. Simple, reliable, mechanical systems. Robust construction tolerating abuse, easy field maintenance and repair. High operational availability, often 70 to 90%. German disadvantages. Complex, fragile mechanical systems. precision construction requiring careful maintenance, difficult field maintenance requiring specialists, low operational availability, often below 50%. The production comparison quantity has a quality all its own. German engineers examining the Sherman had to confront uncomfortable production statistics. Sherman production. By war's end, 49,234 M4 Shermans produced, various models. Production from 11 major manufacturers. Monthly production peak, over 2,000 tanks. Average production time, approximately 2 months from start to delivery. German tank production. By war's end, 6,000 Panzer V Panthers produced, 1,347 Tiger I produced, 492 Tiger II produced. Production scattered across multiple factories. Average production time, 4-6 months from start to delivery. The ratio. The Allies, primarily American Sherman production, outnumbered German heavy tank production by approximately 10, one or more. The strategic implication. From German Panzer Commission Analysis, 1945. American tank production represents industrial capability we cannot match. Even if German tanks are superior individually, which remains debatable given reliability issues, American numerical superiority makes strategic victory through armored warfare impossible. For every Panther or Tiger destroyed, replacement requires months. For every Sherman destroyed, replacement arrives within weeks. American ability to replace losses faster than we can inflict them makes war of attrition unwinnable. The Battle of Araucourt theory meets reality. September 1944, Battle of Araucourt, France. This battle provided empirical test of German tanks, Panthers, versus American tanks, Shermans, under combat conditions. The setup. German 5th Panzer Army, equipped primarily with Panther tanks, attacked American forces near Araucourt. American 4th Armored Division, equipped with Shermans, defended. On paper, Panthers should have won. Better armor, 80 mm sloped frontal armor versus Sherman's 50 mm. Better gun, long 75 mm versus Sherman's medium 75 mm. Better optics. Better crew training, theoretically. The result, American victory, decisively. German forces lost over 200 Panthers. American forces lost approximately 40 Sherman. Germans withdrew and Americans maintained position and counterattacked. Why Panthers lost? Post-battle analysis revealed mechanical failures. Many Panthers broke down before reaching combat. Operational availability was low. Repairs took Panthers out of action for extended periods. Crew training. By September 1944, German tank crew training had deteriorated significantly. Fuel shortages meant limited training. Experienced crews were casualties from Normandy fighting. New crews were inadequately trained. American advantages, high operational availability, most Shermans worked. Experienced crews, 4th Armored had been fighting since Normandy. Superior tactics and coordination. Better logistics and supply. Numerical superiority. Americans could commit more tanks because reliability was higher. Americans could replace losses faster. Panthers' theoretical advantages didn't matter if they couldn't reach combat. The one thing German engineers couldn't believe. After examining captured Shermans and analyzing American production data, German engineers confronted one fact they found almost impossible to accept. American factories built tanks like they built cars. What this meant. The Sherman was designed from the beginning as a mass production vehicle using automotive industry techniques. Assembly line production. Interchangeable parts from multiple suppliers. standardized specifications across manufacturers, quality control through precision manufacturing rather than craftsman adjustment, continuous production improvement, variants improved without stopping production. Why this shocked Germans? German tank production was fundamentally different. Each tank was essentially custom built. Skilled craftsmen assembled tanks individually. Parts often required hand fitting. Quality control depended on craftsman's skill. Production improvements required retooling entire factories. Oberingenieur Muller's conclusion: the Americans have accomplished what we considered impossible: application of automotive mass production techniques to armored vehicle construction. We believed tanks were too complex, too specialized, too individually variable to be mass-produced like automobiles. The Americans proved us wrong. This is not a failure of German engineering. Our tanks are superior individually. This is a failure of German industrial philosophy. We optimize for individual excellence. They optimize for mass production. In total war, mass production defeats individual excellence. The counter-argument: German tanks were better when they worked. It's important to note, German engineers weren't entirely wrong about their tank superiority. When German tanks worked properly and were crewed by trained personnel, they were formidable. Tiger won advantages, could engage and destroy Shermans at ranges where Shermans couldn't respond. Frontal armor was nearly invulnerable to Sherman's 75 mm gun. 88 mm gun could penetrate any Allied tank. Psychological impact on Allied crews was significant. Panther advantages: excellent sloped armor providing protection equal to heavier flat armor. Long 75 mm gun with superior penetration. Good mobility for its weight. When properly maintained, mechanically capable. The problem: these advantages only mattered when the tank was operational, often it wasn't. The crew was trained, increasingly they weren't. The tactical situation favored German strengths, less common as war progressed. Fuel was available, increasingly scarce. Spare parts were available, increasingly unavailable. The reality: a perfectly functioning Tiger with experienced crew could dominate Shermans in open terrain at range, but perfectly functioning Tigers with experienced crews became increasingly rare as the war progressed, while functional Shermans with trained crews remained abundant. The logistics lesson: supply wins wars. German examination of the Sherman revealed another uncomfortable truth. Logistics matters more than specifications. The Sherman's logistical advantages: fuel efficiency. Radial aircraft engine was relatively fuel efficient. Sherman could operate longer on available fuel than German tanks. Parts availability. Standardized parts meant any spare part fit any Sherman. Massive production meant parts were abundant. Simple repairs could be done with available materials. Maintenance simplicity. Crew and battalion mechanics could maintain Shermans. Required basic tools, not specialized equipment. Repair time was short, keeping operational availability high. German logistical disadvantages. Fuel consumption. Tiger and Panther consumed massive quantities of fuel. As fuel became scarce, operational range decreased. Many tanks lost to abandonment due to fuel shortages. Parts availability. Parts often incompatible between different production batches. Manufacturing focused on new tanks, not spare parts. Complex parts required factory-level production. Maintenance complexity, Tarsin, required specialized mechanics. Required specialized tools and equipment. Repair time was long, keeping operational availability low. The strategic impact. From Panzer Commission Analysis, 1945. American focus on logistical sustainability has proven strategically superior to our focus on combat specifications. A Sherman that works is more valuable than a Tiger that doesn't. We optimize for battlefield dominance. They optimize for sustained operations. In prolonged war, sustained operations matters more. The Speer Assessment, Industrial Realization. Albert Speer, Reich Minister of Armaments and War Production, eventually recognized the problem German engineers had identified. Speer's post-war testimony, from Nuremberg testimony and post-war writings. We recognized too late that American industrial methods were fundamentally superior to our approach. We believed that German engineering excellence and craftsmanship would overcome American mass production. We were wrong. American ability to produce thousands of adequate tanks was strategically superior to our ability to produce hundreds of superior tanks. Quality matters, but quantity matters more when the quality difference is not overwhelming. The Sherman was not technically superior to German tanks, but the industrial system that produced the Sherman was incomparably superior to our system. This is what determined the war's outcome. We lost the war in factories, not on battlefields. American factories won the war before American armies did. The von Manteuffel perspective, a tanker's view. General Hasso von Manteuffel, one of Germany's most successful tank commanders, provided another perspective. Post-war assessment. The Sherman was not the best tank of the war. That title might go to the Panther when it worked properly. But the Sherman was the most effective tank of the war because effectiveness means accomplishing your mission. A Panther that breaks down before reaching combat accomplishes nothing. A Sherman that reaches combat and fights accomplishes its mission, even if it's destroyed. American tankers knew their tanks were inferior in direct combat, but they also knew their tanks would work, would be repaired quickly if damaged, and would be replaced if destroyed. This confidence is worth more than superior armor. German tankers feared mechanical failure as much as enemy fire. American tankers only feared enemy fire. This psychological advantage mattered. I would rather have commanded Shermans than Tigers, not because Shermans were better tanks, but because Sherman logistics and reliability were incomparably better. The lessons unlearned, why Germany couldn't adapt. German engineers identified the Sherman's advantages clearly. So why didn't Germany adapt? Structural reasons. Industrial capacity. Germany lacked the industrial base to implement American-style mass production. Factories were smaller and more dispersed. Skilled labor was limited. Resources were increasingly scarce. Allied bombing disrupted production. Doctrinal rigidity. German military doctrine remained focused on tank quality over quantity. Belief that superior individual tanks could overcome numerical inferiority. Emphasis on wonder weapons rather than sustainable production. Hitler's personal interference favoring heavy tanks over reliable medium tanks. Time constraints. By time the lessons were fully recognized, 1944 to 1945, Germany couldn't implement changes. War situation was already desperate. Resources were too limited. Production infrastructure was being destroyed by bombing. Any transition would require halting current production. Ideological blindness. Nazi ideology rejected American industrial methods as inferior. Mass production was seen as crude compared to German craftsmanship. American success was attributed to numerical superiority, not industrial superiority. Accepting American methods as superior meant accepting Nazi racial theories as wrong. The final irony, the tank that won by losing. The ultimate irony is that the Sherman won the war partly by losing battles. The dynamic. In tank versus tank combat, German heavy tanks often won, Tigers and Panthers could destroy Shermans at ranges where Shermans couldn't effectively respond. But these tactical victories didn't lead to strategic success because replacement advantage. Each Sherman destroyed was replaced within weeks. Each Tiger or Panther destroyed took months to replace. Eventually, attrition favored the side that could replace losses faster. Numbers advantage. Multiple Shermans could engage a Tiger from different angles. While the Tiger destroyed some Shermans, others flanked and destroyed the Tiger. Trading 3 Shermans for 1 Tiger was acceptable when you had 10 Shermans and they had 1 Tiger. Operational availability. Shermans were usually operational when needed. German tanks were often inoperational due to mechanical issues. Having 1,000 tanks with 70% operational is better than having 200 tanks with 40% operational. The paradox. German tanks won more individual engagements. American tanks won the war. This wasn't a contradiction. In sustained industrial warfare, strategic sustainability matters more than tactical superiority. The post-war impact. Lessons applied. After the war, tank design internationally incorporated lessons from both German and American approaches. Cold War tank design. Soviet approach. Emphasized mass production, learned from Americans. Emphasized reliability and simplicity, learned from Americans. Emphasized armor and firepower, learned from Germans. Result T-54-55 series, producible in huge quantities, reliable, adequately armed. American approach. Continued emphasis on reliability and logistics. Improved firepower and armor, learning from German tanks. Maintained production efficiency. Result M48/M60 series, balanced approach. British and French approach. Attempted to balance German engineering excellence with American production efficiency. Variable success. Often produced tanks that were sophisticated but expensive and complex. The synthesis. Modern tank design attempts to incorporate adequate combat specifications, firepower, armor, mobility, high reliability and low maintenance requirements, sustainable production costs, logistical supportability. The tension between German perfectionism and American pragmatism continues in military procurement debates today. Conclusion. The tank that shocked Germany. Summer, 1943. German engineers at Kummersdorf Proving Ground examined a captured Sherman tank. They expected to confirm German superiority. They found something that challenged fundamental assumptions. The Sherman wasn't technically superior. Its armor was thinner. Its gun was weaker. Its profile was taller. But the Sherman revealed an industrial and philosophical approach that German engineering couldn't match. Mass production with complete interchangeability. 11 factories producing identical components, parts from any source fitting any tank without modification. Mechanical reliability. Simple, robust systems that work consistently. 5,000 miles of operation without catastrophic failure. Field maintainability. Repairs by ordinary soldiers with basic tools. No specialized mechanics or factory facilities required. Logistical sustainability. Adequate fuel efficiency, abundant spare parts, quick repairs, high operational availability. Strategic sustainability, overwhelming production, rapid replacement of losses. Numbers that couldn't be overcome. German engineers recognized the truth in their reports. We can build better tanks. They can build adequate tanks in overwhelming quantities with advantages we cannot match. This wasn't a failure of German engineering. German tanks were individually superior in many specifications. This was a triumph of American industrial philosophy. The Sherman was designed as a mass production weapon for sustained industrial warfare. In total war, sustained production defeats individual perfection. Logistical superiority defeats technical superiority. Reliability defeats sophistication. The tank that won on paper, the Tiger, the Panther, often lost the war because it couldn't reach the battlefield, couldn't be maintained in the field, couldn't be replaced when lost. The tank that lost on paper, the Sherman, won the war because it worked, could be fixed quickly, and arrived in overwhelming numbers. German engineers understood this. They documented it clearly in their reports. But by the time they fully understood, it was too late. The ice cream served to German POWs in American camps was shocking. The Sherman tank examined at Kummersdorf was more shocking still. Both revealed the same truth. America's strength wasn't in superior weapons or superior soldiers. It was in superior industrial systems that produced abundance. Abundance of food, abundance of tanks, abundance that couldn't be matched, couldn't be countered, couldn't be defeated. The Sherman shocked German engineers because it proved that adequate engineering with superior production defeats superior engineering with adequate production. In war, the tank that works when needed beats the tank that's better when working. The Sherman worked, that's why it won.